All right, we're at section 24.2, potential difference in a uniform field. Let's share the PowerPoint. And we see a positive charge in a downward going electric field. And we see that when a positive charge moves from point A to point B, the electric potential energy of the charge field system decreases. In other words, so when you're if you consider the charge field system, then the uh, electric potential energy at A is much higher than at B. As work is done to move that charge down, it loses electric potential energy. So let's look at here we have VB minus VA is the change in delta V, and that's equal to minus the integral of A to B of E dot ds. Now it is a dot product, so E dot ds is E ds cosine theta, where in this case cosine of 0 degrees. So that's just one, so that becomes the integral of the minus integral of A to B of E dot ds. So delta V is equal to E, you can, since it's a uniform electric field, you can pull the E out, and it's minus E, the integral A to B ds. So delta V is equal to the integral of A to B of ds is just that distance. So delta V is equal to minus E, the electric field, times the distance. The change in electric potential energy is Q delta V is equal to minus Q ED. Now let's look at this in terms of now up here we have an electric charge and an electric field. Here we have a mass in a gravitational field. When an object with mass moves from point A to point B, the gravitational potential energy of the object field system decreases. And this is a good way to think about it, but there's some caveats here, because the gravitational field is always downward when speaking to our reference frame here on Earth. But the electric field can go in any direction. It can go from left to right, right to left. It can even go up. So it's good it's helpful to think of it in terms of gravitational fields, but those can only go so far. Okay, so equipotential surfaces. Now, you all measured equipotential surfaces in your first lab, but let's look at it here. Point B is at a lower electric potential than point A. And points B and C are at the same electrical potential. In other words, they're the same, B and C are the same distance, D, from uh, point A. In other words, the cosine theta, S times the cosine theta gives you D. So all points that are equidistant from A are all at the same electric potential. Delta V equals minus integral of A to B E dot ds equals minus E integral of A to B ds equals minus ES delta the change in electric potential energy is equal to Q delta V equals minus Q E dot ds. And I lost my place here. This indicates, where is it? I thought I had it highlighted, that this is a conservative electric field. Just like the gravitational field is conservative. It doesn't matter the path you take here. It doesn't really matter the path you take to get to change the potential. Okay, let's look here. The labeled points. The labeled points here are the labeled points in the figure are on a series of equipotential surfaces associated with an electric field. Rank from greatest to least the work done by the electric field in a positively charged particle that moves from A to B, from B to C, from C to D, and from D to E. Okay, so if we look, let me see what I've got written here. A to B, they're on the same potential surface. The surfaces are 9 volts, 8 volts, 7 volts, and 6 volts. Those are equipotential surfaces. And so A and B, they are on the same surface, so it's 0. Now, if we look at B to C, that's you have 7 volts. B to C, you have 7 volts minus 9 volts. That's a minus 2 volts. And if we look from C to D, that's a minus 1 volt. And then if we look from D to E, that's going up 1 volt. So in ranking them, there would be B to C, C to D, A to B, and D to E. So from B to C decreases the electric potential by 2 volts. So the electric field performs 2 joules of work on each coulomb of positive charge that moves. Moving from C to D decreases the electric potential by 1 volt. So 1 joule of work is done by the field. It takes no work to move the charge from A to B because the electric potential does not change. A and B are on the same equipotential surface. And then moving from D to E increases the electric potential by 1 volt. Therefore, the field does minus 1 joule of work per unit of positive charge that moves. And that's it for this section, section 24.2. We'll go on to the 24.3 in the next section, in the next little video.